Our next speaker is Dr. Sochol, and he's from mechanical engineering, talking about additive manufacturing in soft robotics.
Awesome. Okay. All right. So hi, everyone. I'm Ryan Sochol from the Department of Mechanical Engineering, as Dr. Sarkar mentioned. And so today I'll be talking about the use of alternative 3D printing approaches for soft robotics.
At certain science fiction depictions of what the future is going to look like with 3D printing, all of a sudden these things become reality.
It's all possible. It's the world of 3D printing, and it's going to change everything.
As big as the steam engine was in its day,
We're talking limitless customization.
as big as the computer was in its day, as big as the internet was in its day.
Printer in every person's home 3 years down the line or 5 years down.
Common in people's homes as the toaster oven.
You print one printer that prints another printer, and it's game over.
So what would you build if you could create anything?
Print any object you can imagine and have it in your hands in just a matter of hours.
It's going to change everything.
All right. So I see some of you are very polite and you've held in your smiles, which you don't need to do here with me. I saw some over here could not hold it in. I don't mind that. This is ridiculous stuff, right? Anyone know why these people are saying stuff like this? I'll give you a hint. It's because they want you to invest in their companies. So, so the one person who was saying like, oh, it's bigger than the internet was in its day, which makes no sense. I thought the internet was still in its day. But he was the CEO of 3D Systems. These were taken back in like around the 2010 to 2012 time point. And what you'll see is that a lot of this bullshit kind of worked, right? So people threw their money down, they invested in these 3D printing stocks, but at some point, right, publicly traded companies have to release their revenues, their profits, and so forth. And we had this kind of wild crash that happened around 2014 for 3D printing companies, and it really kind of never recovered. And so some people will say, Doc Soaks, this happened a long time ago. We've learned our lesson. And I will say, no, we did not. So Desktop Metal is another one. And so this came to market a couple years ago. Everyone said, oh, Desktop Metal, it's got these people from MIT, da 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 da. Everyone threw their money down, stock went up over 30. I sounded like a crazy person because I was telling everyone I could tell, like, what is happening? I don't understand. Finally, the world was right. Their stock crashed, and it's not just like it hasn't recovered. This particular company actually has been threatened with being delisted from the New York Stock Exchange because their stock has been under $1 for so long, which I hope comes to fruition. It will be vindication for me. I spent a good 6 months of my life thinking there was something wrong with the world. Anyways, so what is the reason for this? And I think this kind of comes down to people not understanding what types of applications demand the use of 3D printing and which ones really it makes no sense to use 3D printing. So there are two general rules of thumb that we use in my lab. One is in terms of the number of parts that one is making. So the benefit of conventional methods of manufacturing is that normally the more that you make of something, if you make 20,000, or let's say 20 million of something, that's going to be a whole lot less than just making 2 of something in terms of cost per part. But additive doesn't really have these kind of benefits of scale. Overall, the general costs should have a similar structure where you're just paying for materials, time, and so forth. And so basically, there's this volume break even, which is if you're making a very small, or if you're making a lot of something, use conventional, right? If you hear someone talking about, we're going to make 100 million parts with this additive technology, I want you to put on your critical thinking cap and say, Dr. Sochol doesn't agree with that, and he's going to be mad. All right. But if you're saying I only need a few numbers of these, that's when additive starts to really make sense, right? That's why I got into like rapid prototyping. If you're looking for a killer app, to talk to with your friends at like a cool party, I would say Invisalign is a really great example. So this is a use case where basically your mouth is different from my mouth. And if I'm using Invisalign, in theory, my mouth should be changing month to month to month. And so this is where you need a lot of customizations, a lot of single parts. And this has been a very successful company. I would say aerospace is probably another opportunity where maybe you're only making a handful of rockets. You're not making tens of millions of the same rocket. At least we aren't yet. And so that's another kind of killer app of 3D printing. But the one that I'm more interested in is in terms of something that's a little bit more qualitative or abstract, which is design or geometric complexity. And so typically, the more complex a part design is, and I know that that is like a subjective term, the more it's going to cost to make it using conventional means. But with additive, really, you shouldn't have anything like that. Again, it's just come down to the materials and the time on the machine. So it should stay relatively the same. And so here we have what I'm referring to as complexity break even. And so basically, if you have kind of simple parts, and I know, again, simple, very loose, that's a case where it makes sense to use conventional methods. But the more sophisticated something is, those are cases that really demand additive. And for me in particular, I'm excited about particular things that really you cannot make using conventional means. And so that's this regime over here where there just is no way that I know of to be able to manufacture certain types of components. And so that's where our lab typically operates. I would say that most of the projects we have look something like this, where there's some doctor who comes to us and says, hey, if only we could build blank, then we're able to solve some type of biomedical challenge. And so that's led us to do work in a number of different areas. Obviously, today it's a robotics discussion, so we're going to focus on our work in soft robotics. All right, so there's been a little bit of this from the first talk. Thank you for getting into this. All right, so hopefully I don't have to convince you on my own. Traditional robotics looks something like this, where basically you have these rigid-bodied systems. Often these are controlled using what I would refer to as like electronic means. There are other cases, but I think that's kind of the typical standard. But recently, there's been a lot of interest in what's referred to as soft robotics. And in these cases, you have soft-bodied systems. And one of the ways that these are actuated is using fluidic means. Now, so when I watched this particular scene from Spider-Man, I thought it was really cool they were doing this. And I think it does highlight some of the benefits in terms of the ability to adapt in geometry. But I kind of turned to my wife and I was like, this is a terrible use case. And that's because actually there's an intrinsic safety to soft robotic systems. So if you're trying to use like a soft robotic actuator to like hurt someone, I would say that's like a really dumb idea. So my wife left me and no, things are fine. And so anyways, all right. So there's been a lot of interest in, I would say, the potential of trying to get away from a lot of off-chip controls to getting more of like onboard intelligence with these kind of systems. And so I think our first talk already showed kind of like that issue where you have like the tubing coming out of these robots. This particular paper was how I got into the field. So this is a paper that came out back in 2016. It was a seminal work. I think it totally deserved to be in Nature. This was a big one. And the thing that I thought was really cool about this is that they took a microfluidic chip and they embedded it inside of this Octobot to basically control what's happening like in the robot. And some people like looked at this and they're like, oh, this is silly. It just raises one hand and it raises another hand, tentacles technically. But for me, I thought this was really exciting because fluidic circuitry is something that I personally find very interesting. And the ways of integrating this for soft robotic applications, I think is really exciting. But the part that I looked at when I read through this paper was that there were a couple of very obvious challenges. So one is how do you build integrated fluidic circuits? And then two, how do you integrate those fluidic circuits with the soft robots themselves? And so if we take a look at this paper, this is a manufacturing strategy that I personally would never recommend anyone try to repeat. This is what I would like assign to my enemies, basically. So first you start with multi-layer soft lithography. I don't know if any of you have done that kind of stuff in the clean room before. Me, I hate it. I'm not a fan. So they use it. It's actually even a more sophisticated version of that because you have to like punch holes in the membrane and align the membrane and so forth. Anyway, so they take this process, then they take those, they put them inside of these CNC'd molds. They actually also have like a kind of softer material in there already. And so they're actually doing like a double casting process in here where they have another silicone mixture that they're adding. They're doing degassing, all that kind of stuff. And then they're actually using 3D printing in this case for kind of a pretty interesting concept. And so what they're doing here, let's see if this can click. There we go. So basically, they are printing a sacrificial material. And they're using this in order to connect that circuit to the different arms, they're patterning bladders and all that. And then actually to get it to come out, you have to wait roughly 5 days for it to evaporate out of this device. So this is a pretty rough process. And so our original goal was basically, can we use additive manufacturing or 3D printing to be able to print entire soft robots with fully integrated fluidic circuitry in a single print run? So there are a couple options for that. This is my lab's logo. It's meant to represent kind of the 3 most suitable approaches that would be amenable to this type of application. There are light-based 3D printing techniques, extrusion-based 3D printing techniques, and then also inkjet approaches. And so I think most people, when they hear 3D printing, they're probably thinking about something like this. And indeed, this is something that my lab has done a little bit of work in. I would say the major benefit is material selection. So if everything I'm talking about today, like it's not even comparable. If you want material versatility, this is your approach, hands down. For me, the benefits kind of stop there. This is easily the slowest approach that we've ever used in my lab, like by far. And then also, especially at smaller scales, there's a limit in terms of the geometric versatility, the types of designs that you can build, because the nozzle has to physically be there point by point to put down material. And so another option is what's referred to as material jetting. And in our case, we're using polyjet 3D printing, which is a trademark term. And so this works a lot like a color printer, where instead of printing just one page, we're printing page on top of page. And then just like a color printer where you can combine different colors together, here you can combine different materials together. So you can have your part materials, you can have hard materials and soft materials. You can also have support materials that help the part to build. But then after you're done, you can kind of dissolve those materials away and be left with your final part. And so as a postdoc, I'd actually applied this technique, and we had demonstrated another number of different types of fluidic circuit elements. So there are fluidic capacitors, which are basically just like balloons that inflate. There are fluidic diodes, which are basically kind of like check valves, where basically just one single direction is allowed, but the reverse direction is not allowed. And then we have what we're loosely calling fluidic transistors, but these are really biased in the triode region. So don't think you're going to get any saturation behavior. And so this is something that a number of students from my group ended up trying to kind of put together. And the idea that they came up with was basically, we're going to take designs for fluidic diodes, fluidic transistors, fluidic resistors, which actually you typically don't want, but that's just a channel. We have the actuators actually behave like fluidic capacitors. We have different types of joining elements, and then we have the body features that you can put together. And then you combine these all inside of your CAD software. So for us, we're using SolidWorks. We put it all together. You send the STL file that's all together that has that fluidic circuit inside over to the printer. And then there we go. And then it's going to print it. And again, you can do things like having compliant materials that are connected to rigid materials. Then you have that sacrificial support material. And so this is what the process looks like. If you want, you can go see this printer. It's like it's on the second floor, like right behind us. Basically, for the printing process, the thing that's to note is the taller something is the more time. So this was pretty tall because I thought it'd be cute to have like this big shell, but that shell ended up adding a ton of time to our printing process. But it looked cool, and I was trying to make it look like testudo. I did it. I'm a terrible artist. Anyways, so you can dissolve the support material, and then basically in less than 24 hours from pressing print upstairs, you actually have this, and there's roughly 1 hour of manual labor that's needed to remove that support material. You're left with a soft robot that's ready to use. And so there was another demo that we did here that was kind of fun. I can't go into too much detail in terms of time, but basically the idea is that we had fluidic transistors that activate at different pressures. And so you can basically control these 4 different states using just 2 different pressures, and only one of those pressures is going to be regulated. So the way it works is that initially, if the gate pressure is off and there's a constant source pressure, nothing happens. But if you increase the gate pressure to a low pressure, it's enough to basically activate that first transistor, but not the other one. So the finger's pressed down. If you're playing Super Mario, he walks forward. If you increase it a little bit further, that's enough to get that second one to come down. Now he starts running. And then if you hit a high pressure, Mario will jump. So again, the height is really what changes how much time it's going to take to print. I'm loosely saying less than 4 hours. Really, it's about 3 hours, but like writing 3.1 hours looks ridiculous. And so this was pretty fast and post-processing was fine. And then you can take some cool pictures with black light if you're a dork like me. So this is the setup that we have. Basically, we have our source pressure that's coming in. Again, that's programmed to be constant. And this is all pre-programmed. Then we have a gate pressure, and that's going to be regulated from off to low to medium to high, depending on what we want Mario to do. And then that's going to activate this particular controller to control what happens to Mario. And so I've presented this before. There's like some fun music. If you really want to watch the whole thing, go watch like it on my YouTube channel or something like that. But I think just here, it's just fun to kind of show the example demonstration. But after this, basically, there has been kind of like this emergence of other researchers in the soft robotics space really trying to extend this approach to different types of additive approaches. And so one example is the idea of using material extrusion, those extrusion-based methods, to print these kind of complete soft robots that have that fluidic circuitry that's integrated. You can see the top right, they even like step on it, and then it's able to keep walking. There is some limitation in terms of the geometric capabilities of what's happening. So you'll see these are all very like more block-like. And then the second part is I'm not showing how much time this takes, but actually it takes longer to do this than it does for my process in terms of the entire printing process and getting it off actually is more time than to make the robot that I had, and then we're able to actually have it working. Although ours takes obviously a little bit more like manual work to do it. And so there was a lot of questions of like, all right, like what do you want to do with this technology? And I think that macro scale demo is just kind of more for fun to just show the concept that we could have kind of this gate regulation of multiple states. And so right now we're really working more in terms of trying to scale this down to make certain types of surgical tools. And these are like guide wire microcatheter systems for minimally invasive surgery. And so these are a couple examples. So this is one of my students, Bailey, and me. We went up to Johns Hopkins, and we got to watch some of these procedures. And so this is an example where this person was actually shot like 7 or 8 times. This is Baltimore. And he's fine, but he had some bleeding in his kidney. Somehow he's fine, actually, which is weird. But he was totally okay, except he had some bleeding in his kidneys. So they're delivering coils to stop the bleeding. This is another use case. This is someone who has liver tumors. And the idea is instead of just like dosing your whole body with chemotherapy, which is not great for you, to really just go straight to the tumor itself and actually feed the chemotherapy directly into the vasculature that leads into the kidney. So that's like another application for this. And so there's a number of procedures that do this, but in general, there's some consistent challenges. And one of them is in terms of maneuverability. And so I'm going to show basically this is the kind of vasculature that you're in, but realistically, just navigating this is a genuine challenge. And there's this guide wire that they put in, and the idea is you get the guide wire to where you think you want to go, and then you have this microcatheter you kind of like sheath on top of it to get to the right point. Then you take the guide wire out, and then you can release stuff into the body, whether that's coils or chemo or whatever that might be, through the microcatheter itself. Okay.
Yeah.
And so you're just basically curving the tip. So
Yeah, and there's no real rhyme or reason.
So what I'm showing is basically that when they do this, so you cannot dynamically control the guide wire. What they do is just by hand, the surgeon just kind of looks at it and is like, oh, I'm going to curve it like this. This looks all right. And just puts it into the person's body. That's really the process. Like literally, he took this, he put this right into the person right after this. All right, so that was a surprise to me when I first started learning about this. And so certainly there's a need for on-demand navigation capabilities. Another one is in terms of MRI compatibility. And because a lot of these components are metallic, they're not suitable for MRI, but MRI actually would have much better. So one is it's much safer, especially for pediatric surgeries. But the other one is you get a huge benefit in terms of what you can visualize. And I don't have enough time to go into why this is such a challenge or other means, but basically there are major benefits in terms of being able to have MRI compatible. And that's where soft robotics kind of comes into play. So our current goal basically is to use 3D printing to try to make soft micro robotic surgical instruments that have that integrated microfluidic circuitry, but then they also can be printed in a single print run. And so for this, we're using a light-based approach, and this is called direct laser writing. And the way that this works is that you have a tightly focused pulse laser, and you're scanning it inside of a photoreactive material. And wherever this single focal point touches, it turns from a liquid to a solid, basically it cross-links chemically. So there are some very fast print speeds. And so the state-of-the-art printers can go well into the 1 meter per second range, despite the fact that they have resolutions down to the 100 nanometer range, right? So these are really kind of like major differences in scale. This 100 nanometer range, though, is a little bit of a double-edged sword. And the reason for that is because it's hard to make fluidic interfaces that can connect these kind of components. So initially what we did was we would take a microfluidic device and we would just print right inside of that microfluidic device. And these are examples of like microvasculature and things like that. And you can also do this with electrically conductive components as well. But for today, I really want to kind of focus on this integration of fluidic actuators and microfluidic circuitry. And so one of the ideas that we demonstrated was fluidic diodes. We also did fluidic transistors that are kind of like normally open transistors. But I think the one that's hardest to make, like in this field, if you're interested in getting into it, are what's referred to as normally closed transistors. So these are some of my students who worked on this project. And the idea here is we have these soft actuators. They are interfaced basically downstream with these normally closed 3D microfluidic transistors. This is the structure of what that fluidic transistor looks like at small scale. And so for reference, the height of this channel is 50 microns. So let's say like roughly half of the thickness of a human hair. And so we have this free-floating disk, which you're able to accomplish because you can print so quickly. Then we have this bellowed microstructure, and then we have this micropost on top. So initially, you have a source pressure that comes in, it closes it, there's no flow. But if you activate a gate pressure of sufficient magnitude, it opens this valve and fluid's able to go through. And what's cool about this is you can actually change the diameter of the disk, and very small changes in the diameter actually lead to a really big difference in terms of what pressure these will activate to. And so this is what the printing process looks like, obviously sped up for the sake of time. And then this is a false colored SEM that's just showing the soft actuators. And just for a sense of scale, the size of these actuators is roughly the size of a red blood cell, each of those green things. So we put it all together and we have something like this. It's very similar to the Mario demo, where basically we have this constant source pressure that's coming in. And again, if you apply a low gate pressure, it's enough to activate that first transistor, but not the second. And now fluid's able to come through and activate that first set of grippers. And then if you do a high pressure, you're able to activate that second set of grippers coming in. So with all of this together, one of the things that we were interested in was being able to apply this not inside of a microfluidic chip, but at the end of different types of microcatheters and things like that. So the idea here is something that we refer to as ex situ direct laser writing, where you're putting on top of something. So you put some photomaterial on top of, let's say, some type of medical tubing or a capillary, whatever that might be. And then what we're doing is we're printing right there. And these can have really sophisticated channel architectures, based on whatever it is that you've decided to print, as long as it can satisfy the printing process. You can have really wild stuff like this is readily printable. And so my students have been working on this for a number of applications. You're going to hear one right after this talk. But you can see some examples, like up at the top right, you kind of see just like the scale at which we can produce these types of elements. And this is supposed to be like, hey, we're in the DC region, here are some monuments and stuff like that. And so we've done this for a number of approaches. Again, I'm going to focus only on the soft robotics right now. And so recently, we were fortunate to receive an NIH R01 to basically try to develop this technology for microcatheters where there's surgery inside. The idea is that basically you can actuate which direction it's going to go in based on that gate pressure. And to be honest, it's like relatively new work. So I'm going to just show you exactly where we are, just so you have a sense of where the field is. So these are all recent results. Literally, IEEE RoboSoft was like a month ago. And so we're showing the ability to make custom medical tubing, right? So getting those 2 lines and probably additional one are critical aspects. But getting that repeatedly at small scales is non-trivial. And then these are some example demos of some of the microcatheter components, just showing kind of like those omnidirectional movements. And another one I want to bring to your attention is kind of an interesting concept, which is where you can have these multi-segment actuators. And the idea is that there's certain types of surgery. This one is in collaboration with Children's National and also University of Pittsburgh, where there are certain regions of neonatal hearts that they want to be able to get to. But to do so, you need kind of like an S-shaped bending that is really difficult to be able to navigate with that. But with soft robotics, there's kind of a pathway to do that. So that's another project that we're working on. The other thing I'll mention is we're getting a brand new $600,000 Up Nano Nano 1 3D printer that does this type of technology, but everything